Welcome. In the previous lectures, we introduced ordinary differential equations from an analytical and also geometrical approach. However, we still don't know how to solve them. So today, we will learn how to analytically solve a specific type of ODE that is called separable. Now, what is a separable differential equation? Well, any first order differential equation that can be rewritten in the following way is separable. Now, let's understand this equation. This means a function of y. So everything inside gy means an expression that only depends on y, but not it does not depend on the independent variable. Everything related to the independent variable must be written in the right-hand side of the equation. And this function gy, it's multiplying y prime. So we need to be able to rewrite the equation in this way in order to say that it is separable. An example to clarify this definition could be the following one. Let's say I have a first order ODE, which is y prime t equals the exponential of 3t plus 2y. This is a first order ODE, and we will see it is separable because I'm able to rewrite it in the following way. I can multiply by the exponential of minus 2yt, and what I will get in the right hand side is just this term, because when multiplying by minus 2 times yt, this term will disappear. Yeah. Okay. So this function here is a function that only depends on y, which is multiplying y prime t, and everything in the right hand side only depends on the independent variable t. So that's why we say it is separable. Somehow it means we can separate dependent y and independent t variables, one in each side of the equation. Now these equations are very easy to be solved, and how to solve them is just integrating each side of this first equation 1. We will just integrate each side. So it's like using here the integral of gi with respect to I, integral of ft with respect to t, plus a given constant. This is very important. Remember that if we solve a first order differential equation, there will always be an undetermined constant c. Okay? Now, why is that we can solve the differential equation in this way? Well, here is the proof. We know that we have an ODE that is written in this way, otherwise it's not a separable one. So we will assume it is already written in this way. And now let's assume we have a solution called phi of the differential equation. So if phi is a solution of the differential equation, I can just substitute it inside the differential equation, and what I will get is g3 prime times y prime is going to be phi prime equals f of t. Now I will integrate here with respect to t both sides of the equation, because the left side and the right side, all of them depend on the independent variable t. So what I'm doing is just integrating with respect to time and integrating with respect to time both sides, plus, remember, the integration constant. So this leads us to this equation here. Now the final step is to do a change of variables. If I call y to the function phi t, and I apply what you know as the change of variables to solve an integral, dy is phi prime dt, and you can see here that doing this change of variables, what we will have is that phi prime is called y, and phi prime t dt is nothing more but dy. So this leads to this expression here, yeah? And the right-hand side just remains the same. So in this way, just using the change of variables, we can see that the separable type of ODE can be solved just using this approach. Now let's see some examples. I think it's easier with a numerical example. Let's start with the following ordinary differential equation. We want to find the general solution. That means that we will allow to have a constant there that will be undetermined, and that will give us the general solution of the ODE. Now, this is a separable ODE because we can rewrite it in this way, okay, just using the fact that this is nothing more but this thing, yeah? So I can multiply everything by this value, and I will get this expression here, okay? Well, I don't like to write it here because, okay, I will take it out from here, okay. So we can rewrite it in this way. Now, we know from what we saw in the previous slide that when we have the ODE written in this way, which we have because this is gy, this is f of t, or in this case the independent variable is called x. We could think it in t if it's easier for you now, okay? And as we can write it down in this way, it is separable, and we know that one way to solve it is just to compute the integral in both sides. Now, a trick that I normally use is when I know it is a separable ODE, instead of using Newton's notation for derivatives, I use Leibniz notation for derivatives, which is this one. I know it's exactly the same, it's just a different notation, but it's a way to remember, it's a trick, okay? It's a way to remember how to solve it. And the trick is, okay, I will integrate here, and I will integrate here plus a constant. So you can think like this goes to the other side. This is not true because of course this is a specific notation for the derivative, but just a trick to remember how to solve it, okay? So that's what we will do. We will solve this integral, and we will solve this integral, and we will find the solution. So this is what we do here. We solve this integral, which is this value. We solve this integral, which is very easy, the exponential, and we get what we call the implicit solution. The implicit solution is when you have an equation where there are no derivatives. You can see here that y appears, but not y prime. So this is not a differential equation anymore. It is already solved. So it's the solution. But it's called to be in implicit form because yt is not isolated. When yt is isolated, when we have an expression like yt equals an expression that does not depend on y, then we say that is the explicit solution, okay? In this case, if we want to find the explicit solution, we need to do some algebraic work on this expression. For example, I'm dividing everything by 3 to arrive to this other formula here. Remember here, when we divide by 3, of course we would get, if we divide by 3, we get this, we divide by minus 3, sorry, okay? So if we divide by minus 3, we get plus a minus 2 to y equals minus 2 divided 3 e to the 3x minus, no, sorry, plus 2 divided 3 c. Oh yeah, that's a minus because we are divided by minus 3, okay? Now, you see this term is this term is exactly this term, but what happened here? Well, if we multiply a constant c that can be any real valued number, if we multiply it by a constant, then it is just another constant. So it's very usual to just recall this as another constant, for example c1, which is any real value you want to use. Okay, so now we need to apply logarithms in order to be able to isolate yt from this expression. So we apply the natural logarithm in both sides of the equation. So all this expression goes inside the logarithm, okay? And the natural logarithm and the exponential are inverse functions one to the other. So we get minus 2y in the left-hand side. And in the right-hand side, I cannot simplify it anymore. So I will just leave it like that. And finally, I will divide everything by minus 2. And we will get what is called the explicit solution. Okay, the explicit solution means that yt is isolated. Okay, so this is one example. You have seen in this example that it is going to be very important to remember some properties of the exponential and natural logarithm functions. So here you have a summary slide with some helpful properties that you may need when trying to write the explicit solution, because you need to isolate yt. Now, let's see another example. Now we want to solve the following ordinary differential equation: y prime t equals 4 divided ty. Okay, we want to solve this ODE. The first thing we need to do is it separable? Let's check it out. How can we check it? Well, we need to be able to rewrite it as a function that only depends on y times y prime equal to a function that only depends on t. Is it possible to do that? Well, yes, it's as easy as just writing y in this side. So I will multiply by y and I will get this expression, which of course is a function that only depends on y, that multiplies y prime, and in the right hand side a function that only depends on t. So it is a separable ODE. We can solve it using the integration of each side. What we will do is to write this using Leibniz notation of the derivative of y prime. And then remember that we can solve this by integrating each side and adding a constant c that can be any real value you want. So we arrive to this formula. And now we will compute the integral of y, which is y squared divided 2. And we will solve this integral, which is nothing more but 4 times the natural logarithm. Remember about the absolute value. Okay, the integral of 1 over t is the natural logarithm of the absolute value of t. Okay, so this is important that you remember the absolute value. So very important, not forget the integration constant. Very important, the implicit solution is when you have already done the integrals, you already solved the differential equation, but yt is not isolated, as here, for example. And the explicit solution is when you isolate yt, okay? So in this case, it would be to arrive to this expression. So really isolate y. Now, a last example. Find the general solution of the ODE y prime equals this expression. Now, the first thing is to check if it is separable. Can we write everything that depends on y in the left-hand side? I think we can if we divide the equation by this expression. Yeah, that will lead to 1 divided 2 square root of y minus 2y, that will multiply y prime t, and then in the right hand side I will just have 1 divided t. This term only depends on y, it's gy, which is multiplying y prime t and everything in the right hand side only depends on ft, on the independent variable t. So yeah, it is a separable ODE, and we can solve it using this trick, which is to rewrite it. I like to rewrite it using Leibniz notation, okay? And then I can remember that solving this is as easy as computing the integral of the left-hand side with respect to y and the integral of the right-hand side with respect to t plus an integration constant c that is any real value number you want, okay? So we arrived to this formula that we already have in the slides, okay? Now, this expression we have in the slides with the integrals, okay? So now we need to solve the integrals. In order to solve the differential equation, we need to solve the integrals, okay? We cannot leave it like that. It's very important to solve the integrals. So very important that you review how to solve integrals, okay? Like these ones we have here. For example, the first integral that appears, which is this one, can be solved using a change of variables, as shown here. Okay, this is a very good change of variables in order to solve this differential equation. And then the general solution is very easy to be found. Let me go back. The other integral is very easy. It's just the natural logarithm of t, okay? So that's why we arrive to the general solution that depends on c. In implicit form, that looks like this, okay? Now, if we want to find the explicit solution, in this case we will have a little bit of work because in order to isolate y, as it is inside an absolute value, I will need to check cases depending on if what's inside the absolute value is positive or negative. So that will give us a little bit of extra work, okay? Let me go back. I wanted to point out here that when we divided everything by this expression, of course, when y is equal 0 or y is equal 1, we cannot do that because the denominator would be 0. So for y equals 0 and y equal 1, we need to remember that we must check that cases separately. Are they solutions of the differential equations? We should check that, okay? So here, if we want to find the explicit solution, first we simplify this expression, okay, that we found using the exponential, and we will find the exponential of the natural logarithm is equal to exponential of everything in here. So the exponential and the natural logarithm are inverse functions, so we will get this expression, which is equal to the exponential of everything here is the power of the exponential, which can be divided in two parts, this part times this other part. Now the exponential of a constant is the following, yeah? The exponential function is always positive. Whatever the sign of c, even if it's a negative c, the exponential of c is going to be positive. So we decide to recall, to rewrite the exponential of c as another constant called c1, but it is very important to note that it's always positive. So c1 is any real value number, but it must be positive, okay? So at the end, we arrive to this expression where we simplified the implicit solution expression, but still it is not the explicit solution because yt is not isolated. So in order to do that, we need to study the different cases depending on the signs of the absolute values that appear here, okay? Remember that the cases y equals 0 and y equal 1 have to be studied separately, and we will see now the different cases. Now, let's consider when y is greater than 0 and different from 1, we will have case y smaller than 1, case y greater than 1, which will lead us to these expressions. And of course, we also could study the different cases for the absolute value of t. And at the end, if you study all the possible cases, you arrive to these different expressions, which basically can be summarized as the explicit solution is always going to be 1 plus a constant, let's call it constant 2, divided by t, everything squared. And now this constant can be positive or negative to take into account these cases. So now the C2 could be negative, and in this way we summarize all the possible cases, all the possible solutions. So this is what I wanted to explain today about separable ODEs. Oh, sorry. Here we have to study the case y equals 0 and y equal 1 separately, okay? In these cases, as long as t is different from 0, the ODE has a derivative equal to 0, and therefore the solution is constant. Yt equals 0 and yt equal 1 are solutions. But for t equals 0, the solution doesn't exist. Okay, and you can see that in this plot. For example, when I take this value here, this is 1, y, I don't know what value is this one. Maybe it's, let me see here, minus 1.5 is equal to 1, yeah? So if I use this initial condition, I will have a solution that goes through this point, and that solution is unique. And the same if I took y equals 0, but any initial condition that is given on this line, t equals 0, has no solution. The solution doesn't exist. Yeah, that's what I wanted to explain about separable ODEs. These are the 4 basic steps to correctly solve a separable ODE. We need to know how to write the ODEs as a separable ODE. We need to rewrite it in this way. Then we need to know how to integrals, how the integrals must be solved. So we need to rewrite this in this way. And then we need to be able to solve the integrals and then properly isolate the solution if we want the explicit solution. And finally, if the initial conditions of the problem are given, we will impose them to find the value of C. In the previous examples, we did not give any initial conditions, so we just found the general solution of the ODE that depends on the C value. Okay, I propose you to solve the following exercises 4, 5, and 6, and check it out if you get these solutions. And that's it for today. See you in the next lecture. Bye bye.